All right, so our goal for this problem is to find an expression for the pendulum, and this is a physical pendulum. It has a shape to it, and so we're definitely going to use this formula here for the physical pendulum. Let's think about what we know and what we need to find. I is not going to be a simple thing. That's one of the difficulties of this problem, so we're going to have to derive an expression for I. We do know the mass is capital M. We know the value of little g, but we are going to have to figure out d. All right, so d is going to be from the pivot point to some point. I'm going to guess the center of mass is maybe like around here or something like that. That's going to be our value of d that we're going to have to figure out. So we're going to need to figure out I and the distance to the center of mass point. This is going to involve calculus for both of those things. The thing that's a little new about this problem compared to things that we've done in the past is that the mass is not uniform. This problem talks about something called the linear mass density, which is the ratio between the mass and the length of the object. So it would be capital M over L. That would be something we would know. Now in this case, L is not called L, it's called H from the picture. Okay, so we might need to think about this at some point. But the more important thing is to think about how this relates to a small piece of mass. All right, so this is true, but it's also true that if I just look at a little sliver of mass, it would have a size of dy. Okay, so I'm looking at like a little piece of mass like here that would have a size dy. This mass here would be a small piece of mass dm. So I have this kind of basic statement here. I'm going to rearrange this so that dm is by itself. Okay, so this is actually a statement that is always true. The small piece of mass would equal the linear mass density times dy or possibly dx. In this case, my value of lambda is given to me as c times y. And so this is what I'm going to use in various parts of this problem. All right, so this is the integral form of the formula I equals mr squared, what we use for a particle. So we're going to integrate the distance squared over small amounts of m. But I do need to have these two variables match. You can't do an integral if r is one variable and then your d is not a dr or something like that. So we're going to have to make a little bit of a change here. And this is actually where that linear mass density is going to come into play. So a reminder here, I'm just going to write this over to the side, that dm is equal to, in this case, cy times dy. All right, and so I'm going to make that substitution here into this formula. I'm also not going to use r, so remember that our diagram uses y as the variable. Okay, so I'm going to use y as well. So let's see what we've got going here. We're integrating y squared, and then dm, I'm going to replace it with this expression, cy, and then our new variable of integration is dy. So a reminder, we have this triangle here, and this was our pivot point. So I'm going to call that my 0 point for y, and then we are integrating from that point all the way through to the end of the object. That's where y equals h. So that's going to be our boundaries from y equals 0 to y equals h. And so this is the integral that I want to work through here. I'm just going to kind of go through the steps. I've really got a y cubed. So I've got c times y cubed dy. So when I integrate, I keep my constant. This moves to y to the 4th divided by that new exponent. and I'm going to integrate this from 0 to h. So that means c times h to the 4th over 4 minus 0, so just c times h to the 4th over 4. This is my expression now that I'm going to use for the inertia. Alright, and then the other thing that I need in order to do this calculation is I need to know the distance between the pivot and the center of mass point. Again, I would expect my center of mass to maybe be somewhere around here, closer to the larger mass portion, and so I'm trying to find this distance right here. And that also, again, is assuming that this is my 0 point for y, then that's going to be my value of the position of the center of mass. So this was the formula we used most of the time here when we're working with particles trying to find the location of the center of mass. This is the integral form of that. Because I'm specifically looking in the y direction, let me rewrite this as y center of mass equals integral of y dm over integral of dm. So I'm working kind of with that y direction, and again I'm going to use that statement that I had before, just to recall that dm equals cy dy. Alright, so I'm going to plug that into this integral, and so keep the y, but then also multiply by another cy dy. And then on the bottom, integral of just dm, so cy dy. Now both of these, again, are working along the y-axis, so my bounds are going to be from 0 to h. And then I just need to kind of work through my calculus here. So on the top, this would be c times y squared. That's what I'm integrating. Which means that's c times y cubed over 3. Right. And then on the bottom, I've got cy, so I'm going to raise that from y to the 1 to y to the 2. Alright, and that's also going to be between h and 0. I only needed one step to do that one, so let's see where we're at right now. Again, this is my position of my center of mass. I'm in the y direction. This is also going to give me my value of d for my formula. Okay, so on the top, plugging in the 0 again with the previous one, that's just 0. So this ends up being c times h cubed over 3. And then on the bottom, c times h squared over 2. And so my c's cancel out, some of my h's cancel out. Here's the big idea. My d is going to be h, bring the 2 up to the top, and then over 3. So 2h over 3. Alright, then finally we can sort of put this all together. So a nice big fraction to work from. So my value of I, or my expression for I from before, was c h to the 4th over 4. And then my mass, okay, I know that is capital M G. And then I found d from my most recent calculations here, so that's 2h over 3. Now if I just stop at this point, I've got a problem, because although like some h's would cancel out and so forth, I'm not allowed to have c in my answer. If I look back here, express my answer in terms of h m and physical constant. So I can keep the little g in there, but the c I cannot. All right, so there's got to be something else that I can substitute in order to again, kind of adjust this. Let's look back at the work from here. Okay, and think about this. This term right here, this is the total mass of the object. Okay, you know, think about how when we used to use this formula here, how that bottom part was adding all the masses together. So when we worked our way through here and we got to this expression, this is equal to the total mass. All right. So what I'm going to do here is just make a quick change here, and I'm going to put this expression in there for my value of mass. So let's do that here. Let's rewrite this. 2 times pi square root of CH4, it's supposed to be a little c, CH4 over 4. And then instead of writing m, I'm going to change that to CH squared over 2 times g times 2h over 3. All right, so now I have an expression that I can do just one more simplification. I can get rid of that c, and I'll be good to go. Now, when you take your AP exam, if you were to leave your answer, I'm going to stop kind of partway through here. If you were to leave your answer to this question in this form, okay, so all I did was get rid of my c's. This is an acceptable answer for this question, okay? But I might have trouble sort of answering the next, some later part of the question because I haven't simplified it. So it's kind of up to you. You could leave your answer here as the period like this, and then if you needed to simplify it later, then go ahead and simplify in that section. But let's go ahead and simplify it so that we see what happens. Oops, I left my c in there. I'm sorry. I canceled out my c's, and then I forgot to actually cancel it out here. So I have h to the fourth, and then at the bottom I have h cubed. All right, so that's going to cancel out and just give me an h. I'm going to have a g on the bottom. All right, and then I've got 4 over 4 here, and I've got 6 that I'm going to flip up to the top. So it ends up being 3h over 2g. Pretty simple expression considering how complex this problem was. Alright, so we're trying to see whether the period would change. Let's remind ourselves what that formula looks like. And kind of go from there. So we want to look at the quantities that are on the top and the bottom and see whether they would increase or decrease. Alright, so I changed my little d in the problem to a capital D because that's the variable they're using. I also made my m a capital M. Alright, and those two things are not changing. Okay, it says the second object has the same mass as the first object, and it says that the pivot point is located a distance d above the center of mass, where d is the same distance as for the other one. So the m and the d aren't changing, and the g isn't changing. So the bottom of this fraction doesn't change. So it really just all depends on how I changes. And what I want to be thinking about is, so this is my original object, or my new object. My original object was only half as big. Okay, it's only half as big, and it was pivoting at this point here. And so I can see that the mass of this the second object is further away. That distance always matters most with inertia. And so I could say something like the period is longer for the second pendulum. And it's because, so I need to give a justification, because I is larger, because, this isn't really good grammar, but oh well, I is larger because the mass is further from the pivot. Okay, it's the same amount of mass, but it's further from the pivot. The mass and the distance d do not change. Maybe I'll get rid of my because here. So the period is longer for the second pendulum. I is larger because mass is further from the pivot. That's demonstrating that I understand that important fact about inertia. And I'm also just making it very clear that the mass and the distance d do not change. This is all I need to say for these sorts of justifications. I don't need to do a lot of calculations or anything like that. It is really meant to be thinking about what increases and what decreases, and how that, typically there's going to be a fraction that you're looking at. So you're looking to see, does the numerator increase or decrease? Does the denominator increase or decrease? All right, so now it's asking me to derive. This is going to be something where I will be calculating, where I'll be working with formulas and so forth. Again, they give us some key reminders here. Same mass, same distance d, okay? Something that's going to be really important about that is how the parallel axis theorem works in here, how the shift works in here, okay? So because I'm now very specifically looking at expressions for I, and because this the system does not pivot at its center of mass, what I can do now, okay, because again I've already sort of looked at I about this pivot, I can look at in order to compare the two objects, I can only compare them in terms of about their center of mass. They have the same sort of formula about the center of mass. If I kind of think about this, I wouldn't be writing this necessarily down on my paper, but if this is my second object, my larger object, that's 2h tall, and then I've got my shorter object here, and that's only h. All right, and they have the same mass. They're just different in terms of their length. This is going to have 4 times the inertia of this. All right, all inertia formulas relate to mass and a distance squared. And so if the overall size of the object is doubling, then the overall inertia would be 4 times as big. So just kind of from that thinking, if I just look around the center of mass point, the I around the center of mass for, we'll call this object 2, is going to be 4 times the I about the center of mass for object 1. Okay, and now I can think about the fact that I about point P for object 2, that would be I about the center of mass for object 2 plus the shift. Okay, so that would be the mass, capital M, times, we usually use a little d squared, but this problem has defined that distance as capital D squared. Now, again, this is this. All right, so I can substitute that in. All right, So then let's see if we can think about this and see how we can relate that to I about point P. So I about point P for object 1 would be its I about the center of mass. Okay, so again, I'm using that same variable here, again, plus the shift. But the problem is set up that has the same mass, and we're using the same D, same shift. Okay, and so just make sure of my algebra here. So I'm going to solve for this IP1 minus MD squared. All right, so then I'm going to take this, and I'm going to substitute in for this. So what I'm looking for is 4 times this plus MD squared. All right. So do a little algebra here. So I'm going to 4 times I1. This is going to be negative 4 MD squared plus 1 MD squared, so minus 3 MD squared. That is my expression that I've just derived.